So should I start now, or should we wait to be within the time frame?
I mean, you can start, we are quite flexible. We can always make longer break, talk.
Oh yeah, okay. That's really important.
Yeah, we are
So,
pretty flexible with this thing. So I'm switching off, but I am here.
okay, do you see my screen? Is my screen visible?
Yes.
Oh, perfect. So, dear friends, dear scientists, dear young scientists, and dear old scientists. So we are participating in really interesting project. This project is about the bringing the power of nuclear magnetic resonance, nuclear magnetic relaxation, to the analysis of important things like dairy products. I suppose that many of you already have some positive experience with nuclear magnetic resonance. Nonetheless, I'm here to stress out many different aspects and some minor but really essential features of this method. So today, according to the agenda, we will have several sessions. The first one, the introduction. It will be done by me, and we will go through the understanding what is magnetic resonance phenomenon. Then we will try to understand the physics of it and how practically, in general, it can be applied. Then we are going to have the break where you can drink coffee or do something else. And after the break, we will have the presentation also from Resonance Systems. It will be done mostly by Maria Ivanova. She is the PhD, and she's now also in the audience, and she will talk definitely about practical applications. So it's very important to have a kind of dialogue between those who are listening and those who are talking, because for us it's very important to feel the feedback and to correct maybe the speech for it to be more effective. Then the third session will be held together with the instrument, and our colleagues will show you the device and will practically put some samples. We have prepared some interesting experiments, and you will see in live how things are going on, how you put a sample in a test tube, how you measure, and how you try to estimate what's going on. And then I guess it should be the fourth session where I try to summarize some knowledges. I am expecting to talk a little bit about data processing, and we will consider one of the example how to drive inside a kind of sample and how to derive maximal information about the structure and dynamics. And then again, I am really expecting your feedback, your questions at any time, even if I am talking. So that was the very basic introduction, and now let's go on. So introduction to the very basics of time domain NMR. Well, so during this first session, as I already mentioned, we will talk about different directions of magnetic resonance, and then we will concentrate on the time domain NMR, why it is time domain NMR, why it is not frequency domain NMR. And then we have to go through the basics of the quantum physics and theory that can explain to us as scientists why we observe such signals and why these signals look like they do, and why and how these signals can be converted to something practical, especially for dairy products. And then we will go briefly to some interesting application that will be expanded in the next session by Maria. So let's start from the very much beginning. And we as people who are doing analysis, so our passion in resonance systems and other companies who are producing analytical equipment is just to perform analysis, to understand what's inside. But you know, there are so many different types of analysis. And let's say the first fork is something like we are turning to the left to do a kind of physical analysis. So which is not chemical analysis. Physical, it means that we don't put any chemicals inside, and we try to preserve the sample, and we try to use effects of physics to determine the structure and dynamics. So the first NMR is a kind of physical analysis. Then all analysis which are done by methods of physics can be also subdivided into many different directions. Let's say one of the most let's say useful in industry is, of course, chromatography. Different types of GC, LC, and chromatography together with mass spectrometry. So we are not going to talk about this today. Then there are many other guys like electrophysical analysis, optical analysis, just looking at the structure by your eyes, then using X-ray, using colorimetry to understand the behavior of thermodynamics of samples, and many more. And one of the largest sub-directions of physical analysis is spectroscopy. And then let's look at what spectroscopy is doing. So normally we are considering spectroscopy which is done by photons, not by the elementary particles which have mass, but only by photons, not by electrons, protons, or neutrons, or whatever. So we are talking about photons. We use photons in our daily life when we see something. So this is visible range. The range of frequencies of photons is really wide, and it is starting from very short waves, but high frequency X-ray. Then there is a kind of ultraviolet spectroscopy. Then there is the spectroscopy in the range of visible wavelength, and then we go on with the decreasing of frequency. Then there is a huge area which is infrared spectroscopy, which deals with the mechanical oscillations and vibrations. And our visible is, of course, you know, these are transitions of electrons within atoms. And then going down, we have a kind of microwave. So this is very high radio frequency. And somehow about wavelength between 1 meter and 5 meters. So these are very long photons. We have the range that is occupied by a nuclear magnetic resonance. And only a very tiny range of this bigger range is relating to the time domain NMR. So looking at this spectrum, you know, the energy of photon is proportional to the frequency. So I suppose you might have somehow dealt with X-ray when you go and you check your bones, for example. And then you know that it's not really good idea to be exposed to the X-rays for a long time, because these photons they have strong energy, and then that can distract your body because the energy is high, because the frequency is high. And as you see in the frequency ranges, NMR and time domain NMR, this is, let's say, one of the methods of the physical methods that are involving very low frequency. It means that the energy is totally low. It is absolutely not dangerous to our body, to any types of living health. So even if you talk by the cell phone, you spoil your body much 10 times stronger than if you are dealing with a nuclear magnetic resonance. So this is very important factor. Okay, going on. And then this NMR, let's consider this NMR. Then we have some subdirections. The most involved in not only an NMR spectroscopy, but also within the chemical analysis, it is high resolution NMR spectroscopy. This method is, let's say, it attracted the largest amount of Nobel Prizes, and it is totally informative. I would say it is one of the most, maybe even the most informative spectroscopical method for analyzing of structure, and where you can see direct chemistry, where you can see direct interaction between definite chemical groups. And but we are not dealing with high resolution mass spectroscopy because this is not the topic of our grant. And there are, let's say, there are two more big directions, which is in the middle is a low field relaxometry, and also that involves time domain NMR that we will talk today about, and NMR imaging. In other words, it is called magnetic resonance imaging, MRI. There are also, these guys are also used in clinics, in hospitals, to analyze the body content. So, understanding from the previous slide, you can be sure that when you come inside the MRI scanner, you definitely are totally safe. Well, so out of all these guys, we are considering very narrow range of frequencies, and we will talk about relaxometry. So the word relaxometry, it is something that is based on the measurement of relaxation. And this, you know, this can be considered as the relaxometry with cyclone of magnetic field. This is fast field cyclone relaxometry, or just the measurement of relaxation, which is called just relaxometry, or just to be definite, also time domain NMR. Time domain NMR is the name that is used opposite to frequency domain NMR. NMR spectroscopy, for people to understand that these are two different approaches to analyze samples. So that was a kind of introduction to the location of NMR, the position of time domain NMR inside the whole bunch of analytical methods. And now let's start talking about the physics. So we are talking about so in any spectroscopical approach, we are dealing with transitions. And these transitions are happening between levels. Like already mentioned in, let's say, visible spectroscopy, these transitions are between the levels of electrons in atoms. They are quite of high frequency. And here we are dealing with a transition between so-called Zeeman levels. So just imagine that you in your body have some guys like are enumerated in this table. The most abundant is hydrogen 1. It is in water, it is in tissues, in peptides, in DNA, and so on. So we all have enough paramagnetic nuclei. So just very small remark. You cannot observe NMR on any types of nuclei. You can observe only on some isotopes of each nuclei, which have a possibility to be paramagnetic, to be for their levels to be splitted inside the magnetic field. So since it's nuclear, magnetic, and resonance. Nuclear, it means that we are looking at nuclei. It doesn't deal anyhow with the nuclear physics, nuclear atomic bombs. This is different, but this is about nuclei. Biomagnetic, because we are taking samples inside the magnet. which produces a magnetic field which is normally called B0. And then within this magnetic field, the levels of nuclei, they are of those nuclei who have paramagnetic effect, they can be splitted. And the splitting of the levels is proportional to the magnetic field. It means that if you don't put anything inside the magnet, there is no split of the levels. And if you put in a magnet of, let's say, 1 Tesla, then you will have the splitting of 42.5.6 megahertz. This is very low frequency, as I already mentioned in slides before, very low frequency. And then there are transitions, and if you apply if you put a coil and you try to excite the sample, you will not get anything unless your frequency is equal to this so-called Larmor frequency. That's why this effect can be observed only when frequencies are matched. So matching of frequencies is called resonance. So nuclear magnetic resonance. So what is happening inside the magnet? Let's just consider hydrogen 1 nuclei, which we will call just protons for simplicity in our following discussion. So just imagine these protons, they are inside the magnetic field. And according to the very basics of quantum physics, when they are inside the magnetic field, the level of nuclei is being splitted. What it means in practice? Each of these guys, each of these nuclei, they possess such such value as the magnetic spin. And magnetic spin moment can be observed, can be detected only when it is along the magnetic field or opposite magnetic field, which here we are talking about the spins of protons. So there are only two directions. And when you put a kind of sample with let's say, room temperature, most of the spins will be aligned along the magnetic field. And some minor amount will look backwards, will be directed to opposite direction. And if we summarize all these arrows that are looking to the right, and then subtract all arrows that are looking to the left, then we will get a kind of vector of magnetization. And this vector, then we can play with this vector. We can try to implement different excitations, and we can try to observe how this vector is evolving. But I don't want to, before switching to the next slide, I will talk a little bit about real atoms. In real atoms, there are hydrogen nuclei, and of course, since we are talking about molecules, and there are always a kind of cloud structure which electrons are forming. And these clouds, there are currents because electrons are moving in, electrons are moving in atoms, and electrons are moving within molecules. And their movement, they make a kind of current. Since the charge is moving, then there is a current. And according to the basic law of the how do we call it? The law of magnetic flow, the direction of magnetic flow. So these electrons start moving to prevent the changing of magnetic field on the proton. It means that these electrons will create a shielding, will somehow decrease the magnetic field on the proton, the magnetic field that is outer. So we have, let's say, the field of the magnet, and then we have the magnetic field which is shielding, which causes so-called chemical shifts. And then also these guys, since they have magnetic moment, they are always magnets themselves. And all neighbors especially in solids, they're located close to each other and they interact with each other and they make the local field. So, and the observed frequency of a definite nucleus will be defined by the magnetic field of the magnet, and then local magnetic fields from neighbors, and the shielding effect from electrons. Then we can consider all of these guys. Chemical shifts. This is, let's say, the main number that can be derived from high resolution NMR. Then different chemical structures, they have different patterns of spectra, and so this is very much direct method to analyze the chemical structure. Then there is so-called weak interactions where this shielding is affected by the neighbors, and then we have so-called J coupling. J coupling together with the just shielding, they form the spectrum, the high resolution spectrum. And so we are again I show you the equation that was shown before. And this shield, this shielding magnetic field, it is proportional to the current that electrons are making. And this opposite current is proportional to the outer magnetic field. So if we don't apply the B0, the magnet, so there will not be a special current that is trying to decrease the B0 on a nucleus. It means that all these chemical shifts will be as larger, as bigger the magnetic field it is. That's why for the high resolution NMR, it is very much recommended to have the strong magnet. So, and here I am showing to you the evolution of different NMR spectroscopy magnets. Initially, they were just simple resistive coil magnets, and then already, I guess, 30 years ago, or even more, the guys implemented the superconductive magnets where the current is horribly high and the field is much higher. And if you try to become a chemist and publish the article of the high impact analytical journal at the now in the area of chemistry, so the editorial board will not accept the results that are made on the magnets which are lower than 600 megahertz for protons. So the message that I want to tell here is based on that for the NMR spectroscopy, it's very important to have lots of money and to buy the expensive magnets. And the more expensive magnet, the larger this shift in hertz, and the better resolution you can get. So just for understanding the physics, this. I guess everybody tried. Many of you might try ethanol. So it has. When we look at hydrogens, we see that there are 3 different hydrogens that are chemically different. These 3 guys, they are aliphatic, and there are 3 bonds. These 2 guys, they are also aliphatic, but there are only 2 bonds for these 2. And this guy, it is just attached to not to carbon, but to oxygen. So the structure of electron clouds is different, and then you are getting different lines within the spectrum. And the intensity, the area, and which line for each line is proportional to amount of these hydrogens. So here there is only 1 guy, and the area will be, let's say, 1. And here there are 2 guys, and the area will be twice bigger. And for this line, area will be 3 times larger. But this fine splitting, it is about the orientation of different spins, and this is J coupling, and altogether this spectrum tells to any spectroscopy that you are dealing with ethanol, for example. And as I already mentioned, there are tables with these chemical shifts, and so I guess the high resolution NMR is really nice and really accurate and elegant method to retrieve the structure of chemical structure of things. But again, coming to time domain NMR, this is already different story. First, the magnets are not super conductive because there is no need to do strong and very much expensive magnets. Normally, the magnets are being produced out of the permanent magnets, mostly produced in China, because they have lots of mines with magnetic materials. And the homogeneity of the magnetic field B0 in a time domain NMR instrument normally is worse than the homogeneity of B0 in high resolution NMR magnet. It means that if we put ethanol in a time domain NMR machine, we will not get this. We will not get this resolution. That's why it's not called high resolution. We will get just a kind of line that is white, and likely you will not see the triplet in the spectrum. Then what's going on, how we observe this NMR? So we have the magnet and we have the probe that accommodates a sample. And within the probe, there is a coil. There is a radio frequency coil where during excitation, we put the strong current, and this strong current, once it is going through the coil, this solenoid produces another magnetic field, which is called B1. And it is normally done with the B1 is orthogonal, is perpendicular to B0. And then we create this excitation magnetic field B1. And after excitation, we put we excite the sample, and we then make the excitation down. And this excitation is radio frequency. This radio frequency, as I mentioned already, should be calculated according to the frequency of the magnet. So we put the pulse excitation, and then we start observing the relaxation. And the way how these magnetized spins are reacting during relaxation, this way tells us about the properties of sample. And this is the, let's say, the basic schematics of making the time domain NMR experiment. We excite, and then the sample is excited, and then it relaxes, and we observe the relaxation, and out of the relaxation patterns, we try to get information. So as I already mentioned you before, so just in the equilibrium, most of the spins, they are on the basic level. So it means that they are looking towards the magnetic field. Some of the spins are looking opposite, and the difference in population is rising with lowering the temperature or increasing the magnetic field. So, but implementing different types of pulses, we can play with these spins. So in this situation, there is a slight magnetization around this axis. So these guys are looking to this direction, these guys are looking down, but in general, the resulting vector is of magnetization looking towards this direction, that direction. That is the direction of the B0 from north to south. When we implement the radio frequency pulse, so we can pick up the duration of the pulse in such a way that all this nuclear magnetization will not look towards the z-axis, it will look within the xy plane, and then we can make the equalization of populations, and so this is called so-called rotation of magnetization by 90 degrees. Or we can pick up such duration or amplitude of the oscillating magnetic field to make this magnetization looking down against the z-axis. And then we can play with the direction of the magnetization. And this is a very important slide. Please try to take it inside of your brain, inside of your body. This is like this is like you maybe already have heard that in time domain NMR we are talking about also relaxation times, and there are two relaxation times. There are T1 and T2. T1 and T2, and T1 is the time which is required for the system to start coming to equilibrium with the magnetization along the magnetic field. This is so-called spin lattice or transverse or longitudinal relaxation. Longitudinal T1 spin lattice. But when we rotate this implement so-called 90 pulse, then we also will observe the relaxation within the XY plane. And this type of relaxation is called transverse, and it has the parameter of T2, and also, in other words, it's spin-spin relaxation types. This is not so much complicated. Just there are two different types of relaxation times, and one of the since T1 tells you about the common trend of coming to the thermal equilibrium. So this process is, let's say, the most long process. That is why the local relaxation within the spin system cannot be longer than the total relaxation. That's why T1 is always not less than T2. So that with this slide, as you see, we have made a kind of understanding, a kind of introduction of relaxation times, but we will talk about these relaxation times all the day today. Then how things are evolving, how things are relaxing. So the behavior of the magnetization, let me remind you, the magnetization is the excess of spins between these two levels. Let's say the difference of spins multiplied by the direction. The magnetization evolves with the time, and macroscopically, this evolution can be described with a system of so-called block equations. The solutions for these differential equations are, for the simple system, they are very simple. They are about the exponential functions. And so the transverse magnetization, the T2 relaxation, happens with the, normally in the ideal condition, happens with the exponential law, and the characteristic time is so-called T2. And this guy which is oscillating, you know, since we have this imaginary part, this is how the vector of magnetization is precessing or rotating within the XY plane. But let's say the envelope of this guy, of this sine and cosine, it is exponential with the characteristic time of T2. And the amplitude of this exponent is proportional to amount of hydrogens within the sample. And for the longitudinal relaxation, we don't have any oscillation. We have only the process where we let's say, give the 90 pulse, and then there's the relaxation. The 90 pulse, we have zero Z component magnetization, and then it starts to relax and come to equilibrium. And it also obeys the exponential law, but the characteristic time is called T1. So that is, let's say, the very, very much basic words about the time domain NMR. And then what's the difference? Why we are doing time domain NMR? Is it only because of the cost of the magnet? Not. In low field NMR, in low field and in time domain NMR, we have some problems and we have some advantages. And let's now try to consider the disadvantage comparing to the high resolution NMR spectroscopy. First, this is the so-called signal-to-noise ratio. The good and inexpensive high-resolution device has much better signal-to-noise ratio because the magnetic field is higher, and this dependence is nearly I don't know, this with a very high power. The stronger field you apply, the stronger signal, the much stronger signal you can get. And then if we compare two devices, which is operating at 20 megahertz, it's a typical spin mate from resonance systems. And these guys from our friends from Brooker, it's operate at 400 megahertz. So the difference in the signal to noise ratio will be about 2,000 times. So we really get the loss of the signal. But you know why the time domain NMR is becoming more and more popular? That is because the electronics and technology is evolving and becomes much better. And you know, comparing the signals that we getting now with one scan with what we could get 30 or 25 years ago, it's just incomparable. So let's say this problem somehow is being solved. One thing, and the other thing, normally in high resolution, you are using small test tubes because you need to provide the uniform magnetic field in a small volume. In the time domain NMR experiment, you can use tubes much bigger, and the amount of samples is larger. So you also somehow resolve the issue with the signal to noise ratio. The other thing is inhomogeneity. As I already told you, the expensive high-resolution spectroscopy magnet, it has perfect magnet. It is a perfect magnet, and in the time domain NMR device, since it's not so much that much expensive, it normally does not have a special shimming system, and homogeneity in time domain experiments of the magnet of the B0 is much lower. But what but you know, in many cases it is even better, and it gives you much better stability of the signal, and just the issues of observing direct T2 or T2 with a star, it can be somehow and can be easily resolved with the so-called echo technique. So we will talk about echo techniques also today. So let's say these are two main guys, and the other drawback and then the other challenge in time domain NMR, when you are doing time domain NMR of solids, it is so-called reading time of the probe. So we normally, when we are coming about this structure, we have the transmitter, which excites, we have the receiver that receives the relaxation signal, we have the coil. And normally the pulse of transmitter must be very strong. On the coil, it is somehow a few kilovolts of the energy, few kilovolts of the voltages across the coil. And when we detect signal, it is few microvolts. So you know the response is much lower. And if you implement very strong pulse, then for some period of time, the probe, the coil within the magnet, it has its own, let's say, relaxation period, and it should somehow come to equilibrium. And normally this is within 5 to 10 microseconds for a 10 millimeter coil. There is a ringing of the probe. And this ring brings some problems when you are looking at the solid samples, but we will discuss this. And you know, since already many years, there are also techniques somehow to overcome this problem. So that was a kind of, I guess, introduction, very brief introduction. What I would do now, if there are some questions, and I would make a break for 1 or 2 minutes, just for your brain to be ready to talk about some theory and so on, and some applications. Danuta, what do you think? 3 minutes break. Will it be 3-4 minutes break?
5 minutes break. How about
5 minutes break, and then before I start next time, I will go smoke. Before I start next time, if there are any questions, I would be happy to answer them. And now we have 5 minutes break.
Thanks a lot.
Mm-hmm. Can we?
It seems that you gave us, fantastic introduction to NMR. not
To
only
NMR,
time
to NMR
domain. Yeah,
spectroscopy. Yeah,
repetition is very useful. Okay, let us have 5 minutes break.
yeah. Let's have 5 minutes. Yeah.
Okay. It seems that Leonid needs some time more.
I am okay. I have done my smoking.
Because there's a question to you in the
Okay.
chat.
Okay, let me try open the chat.
Could you please explain indirect spin-spin J coupling and direct spin-spin bipolar coupling?
It's a very great question.
Yes.
Very good question.
Very, very useful.
Very, very useful. I will talk about this indirect and direct. Have we already started?
I think so.
Yeah, okay. Let's then I think you see my screen.
Yes, we do.
Well, the indirect and direct. So direct, when these guys are interacting with each other directly. Just imagine you have, these hydrogen nuclei, these protons, they are located quite close to each other, especially in solid states. And in solid state, they even don't really move within their locations. And they behave like magnets. And let's imagine your neighbor, he has the magnet and he is influencing you directly. For example, you live in a house and you have a dog and you have a neighbor. Let's say neighbor wants to communicate with you and neighbor calls directly to your phone. This is direct interaction. And indirect, it means the neighbor is influencing your dog and dog starts to bark, starts to cry, and the dog finally influencing you. So this indirect. So for indirect, a neighbor communicates to the electrons, and then these electrons start shielding differently. For example, I think actually they should be really more splitting on the OH group. But you know, for this guy, for these three protons, they can look. We already discussed that the spin 1/2, it can be directed along the field and opposite the field. And there are how many different combinations when the three look in one direction, when the three look in opposite direction, then two in one and one is opposite, two is opposite to one, and then there are different populations of these combinations. And each of the combinations changes the electron structure of a neighbor. And then the nucleus, which is within this neighboring, it replies with different with some multiplet, and this is called indirect spin-spin communication. And in other words, it's this J coupling. For direct, it is also direct spin-spin. They are called dipolar interactions, and we will talk about mostly dipolar interactions because this is the topic of our time domain NMR. We are dealing with a dipolar Hamiltonian. Very good questions. Very good question. How can I move this? Well, this is exactly what I'm gonna talk about. So all the energy levels can be described by some mathematics. And this math is actually quite straightforward. The energy operator in quantum physics is called Hamiltonian. And each of the guys, each of the spins that are participating in NMR, they are influenced by different types of Hamiltonians, by the main magnet and by the neighbors through the electrons. This is the Zeeman part of Hamiltonian. Zeeman is the main frequency, and the Zeeman is split into the chemical shifts. Then radio frequency Hamiltonian, that is what is used to excite spins, and it's not stable. You just give the pulse, and after this pulse, this radio frequency guy is zero. Then indirect spin, that according to the question, and direct spin. Direct interactions are also called dipolar. And since we are talking about dipoles, the interaction is, let's say, the interaction energy, the interaction power, the interaction force, let's say, is dependent on the field on the neighbor, is opposite, or not how it is in English, reversely proportional to the cubic distance between nuclei. And then this expression can be expanded into many contributions. We are talking about only Hamiltonian of the dipolar interaction of the direct spin-spin, and this interaction can be expanded. If we only talk about two spins, can expand it to lots of formulas, to lots of equations, and actually, again, for simplicity, we can present them as a kind of dipolar alphabet, especially considering that there are just direct interactions like for magnets, and then from quantum physics there are lots of indirect things, like, let's say, zero quantum, nothing is happening. So this part of Hamiltonian is responsible for zero quantum transitions. They are very much useful when we are talking about spin diffusion. Then there are the guys. What else I need to talk about? There are the guys which are responsible for changing of quantum order by two rising and two lowering operators, spin operators, that are responsible not only for flipping spins, but flipping spins that are happening simultaneously. Just imagine two nuclei and their spins flipping together. So it is like two quants, two photons are being irradiated. It means that in these terms, the transition is called double quantum transition. There are two quants on two photons on the Larmor frequency, and the evolution of the magnetization is not described by the Hamiltonian. Hamiltonian is the interaction, and the evolution is normally described by so-called equation of von Neumann, Liouville von Neumann equation. It is really reminds us Schrödinger equation, which is normally built for wave function of simple systems, and for complicated system, the wave functions is being substituted by the linear by the combination of quantum states, and it's called density operator or density matrix. We are not going to talk about lots about this complicated math, but this is for you just to understand that behind all the spin relaxation processes, there is a kind of math, and this math can be somehow resolved directly or with some simplifications. Since we are now, for simplicity, considering just two spin systems, and these two spins can be oriented in some not, they can look all along the field, all opposite the field, and they can look in the mixed conditions. And here the diagonal of this density matrix will evolve according to the spin lattice relaxation, according to the longitudinal relaxation, because now all these guys they contribute somehow to their own states. Everything which is related to the changing of, let's say, one quantum, single quantum transition, irradiation of one photon, they are called transverse relaxation contribution into density matrix. And since this is a kind of differential equation of the first order with imaginary part, the result will be harmonic function, and the result is actually the exponential decay with some oscillation. Then as I already told you, zero quantum transitions when nothing is changing in the quantum order, and double quantum transition when these two guys are flipping simultaneously. And if we want to build the relaxation model, we just use this equation and we try to solve it. Let's say for single quantum transition, we will get something like a block equation. For double quantum transition, we will get something else. But we need also to take to account, to consideration, the dynamics. And the dynamics can be somehow estimated by the let's start with the simplest approach of the single correlation time. What is correlation function? Dynamics, how they are moving with respect to each other. If the particle is moving, so motions can be different. This can be vibrations, this can be translational motion, this can be rotational, or this can be more complicated shapes. But for any simple, let's say, just imagine that there is a particle, and this particle is moving translationally in one direction. And the time that is required for this particle to pass the distance, which is equal to the dimension of this particle, is in generally something like a correlation time. It means if the correlation time is short, then the particle is moving fast. If the correlation time is long, then the particle is moving slowly. And the graph that shows how they imagine, so just imagine one particle is sitting and the other is passing by. And this graph somehow represents how they don't overlap at all. It is about zero, and they overlap completely. This is zero time. And then the overlapping again goes to the zero level because the particle is moving away. And this shape of the correlation function can be normally, for simple system, it has a kind of Lorentzian line shape. And if we perform the Fourier transform, we will get the frequency domain representation of this correlation function, which is called energy spectrum of a sample. And the energy spectrum of a sample, so the wider range of the frequency of energy spectrum, the more narrow exponential correlation function we have. Actually, the shape of the Lorentzian shape is something about the this shape of the energy spectrum. So if you take any liquid or any solids, the protons, the hydrogens within it are always moving. And but they move with different frequencies and with different speeds. For example, if you take solids, they are moving quite slowly. And we talk about correlation times of order of microseconds and longer. If you take a liquid and you heat this liquid, for example, boiling water, these guys are moving really fast, and then you are talking about 10 in minus 12th power of seconds of correlation time. So it's million times faster than for solids. Then somehow bringing together the structure, which is described by the Hamiltonian, and the dynamics, which is described by the correlation times and energy spectrum, we can come to the description of relaxation rates that depend that when you solve the main equation, so your Hamiltonian will somehow take into account, and your location or your particles will be described with the motion theory. Then some simplification allow using so-called semi-classical approximation approach, which is which can be represented in the form of the relaxation rate. It is 1 over T1, 1 over T2, can be written for two spin systems with such simple solution. So again, we are taking the main equation, we are implementing the Hamiltonian, we are bringing the behavior of these guys of this location depending on the temperature, so we implement the motion, and then we try to solve this equation, and then we get the exponential solution here. And the characteristic rates of these exponents will be expressed with a simple, two simple formula, where M2 is the structure, the so-called static second moment, which can be calculated from the positions of the spins, and J is energy spectrum that we just were talking about, which is directly correlated to the correlation function. So, and to have even simpler simplification, even further simplification, we can substitute the energy spectrum with the Lorentzian line when we just consider correlation function as a simple exponent. And so, as I said already, second moment, static second moment is a structure, and this is dynamics. And in the simplest way, from the semi-classical Redfield approach, we are coming to the simplification, which is called Blombergian personal perron theory, or in other words, Solomon equation, where these spectra are substituted by the ready solutions from here. And this approach, this is very practical approach, Blombergian theory, it is absolutely widely used in fast field cycling and NMR relaxometry that you will talk about tomorrow. And of course, it is also used in the classical time domain experiment, where we have some ideas of relaxation times. So relaxation time is 1 over relaxation rate. So this is 1 over T1 is equal to this, and 1 over T2 is equal to this. So again, having these horrible equations and the motions described by the correlation function, we are coming to the very much simplified solution within Blombergian theory. And then within this theory, if we make a plot of the relaxation times against this variable, this is the frequency multiplied, Larmor frequency multiplied by the correlation time, we will get the shapes that are published in all the textbooks. These shapes, from the NMR point of view, it has the region where T1 is equal to T2, and from NMR point of view, this is liquid. It might not be really liquid depending on the frequency, but for NMR it is liquid, because for NMR liquid starts when your T1 starts be equal to T2, and for solids they behave in opposite ways. So T2 becomes even smaller when rising of correlation time, when the correlation time becomes longer, then the motions are more slow. The more slow motion, the lower T2 and the higher T1. So T1 behaves actually equally for solids and for liquids, but in opposite directions. Well, and now we are finally coming from all these discussions, we are finally coming to a real instrument and what we really observe if we take a sample and put it inside the system. So now we can be calm, we can be happy, we have the basic theoretical background just to talk about the behavior of different relaxation. This is important thing when a spectroscopy people, when those who are doing NMR all their life and do NMR spectroscopy with expensive machines, they normally normally think about time domain NMR people that everything is very simple in time domain NMR. You pull the sample, you measure T2, and then you are happy. Not at all, because samples, it is, for most of the high resolution NMR machine, the sample must be liquid. And if you have a solid state probe that is special, also expensive probe for the high resolution device, there you also try to kill these dipolar interactions. But in time domain NMR, this dipolar Hamiltonian is the source of information. So in high resolution, this guy is bad, and people are trying to kill it maximally, to look more on the Zeeman part and the J coupling. But for NMR relaxation and for time domain NMR, this artifact becomes the main source of the information. So this is the principal difference between two methods: high resolution, low resolution. So we are talking about relaxation time, and just if you take a sample of something, if you take I don't know, we are all now the diary people. If you take powdered milk and put inside the test tube, what we will do today after lunch, you will see something that decays fast and something that decays slow. You make the typical T2 experiment, but you will see at least two components. Something that decays fast, we are coming here. Fast, it means short T2. Short T2 corresponds to slow motions. It means that fast component is something solid, something rigid. And the slow component, the T2 is smaller, and so the motions are faster. Means it normally represents something that is soft or something that is liquid. So you put something inside some sample inside the instrument, and you immediately get a kind of response. What's going there? So I don't know because Maria will have a we will have this type of discussion after my talk. But I will anyway. When you repeat something, you take it much better and for much longer time. Some simple standard applications. For example, solid fat content in fats. You measure a kind of FID experiment. So Maria will talk about this experiment in more details. And you, in the relaxation, you see two components, which is fast and which is slow. And you attribute fast component to the solid fraction and the slow component to the liquid fraction. And then with much simpler mathematics than for quantum mechanics, you just calculate the difference, the different contribution of liquid and solid, and then you get this SFC solid. So you take a battery, you don't know what part of this battery is liquid and what part of this battery is solid. But when you put it inside the NMR machine, you immediately will see different contributions. Similar approach is used in oil and moisture in seeds, but this is a dairy product, so I guess Maria will talk about this more. Then very simple NMR experiment when you look at different proportions of hydrogens. But when you investigate rock cores, you take a core, you saturate it with a liquid, with a fluid, and then put inside the NMR machine, and then you measure the relaxation, and then you get the distribution of relaxation times. So as we already discussed, the shorter relaxation time, the more slow motions there are. And if you get a kind of distribution of relaxation times, it means that those guys who have less so the values of T2 that are smaller, they represent pores with a smaller diameter. And there is a, let's say, linear correlation between the T2 and the pore. So the bigger pore, the more free fluid will be within this pore, and so you can get the distribution of relaxation times. Then another very simple method to analyze the content. You implement pulse sequence, special pulse sequence, and you get signal from the liquid and you get signal from a solid, and then you can normalize one by another, and then the more oil pickup on yarn, on tissues, on threads, then you have the strongest signal. Now I'm going to show you the video. The video from our friends. We supply some part of our hardware to this interesting company in Finland. We supply boards, and they are making the final instrument, and they are measuring just humidity. I want you to watch this video. This will be, I guess, quite simple to understand. Then we will continue. It's short. Wait. So I will shorten. So here again, water has much stronger mobility than the wood, and then you differentiate contribution of water because it has different relaxation time, and then you see the quite smart device is done, and I think nearly 100 of these guys are already installed in different factories to analyze the moisture content. Well, then I guess before going further, that's a very critical part of the talk, and I guess I have something like 10 minutes. So let's briefly look at different types of measurement that can be done. There are absolute amplitude, relative amplitude, and relaxation times measured. Most of them are used in simple methods that are of time domain NMR to analyze structure and dynamics. So absolute amplitude, relative amplitude, and relaxation times. As we already discussed, amplitude is proportional to amount of hydrogen. Relaxation time is dependent on the structure and on the dynamics. So absolute measurements, it is something like you are taking a sample and measure how much signal you get from this sample. And then, of course, you need to do some normalizing. So normally it's normalizing by the mass, by the weighting, or normalizing by the volume. You put a sample, you get the mass, you measure, you divide by mass, and then you measure amplitude. And then you get the calibration, and then your method is ready. And it works for really many guys, for water content, for oil moisture content, seeds, hydrogen content, fuel, spin finish. total fat content, proton density for multiple tasks. So actually for fat and for water in milk powders, it also can be easily estimated. So absolute amplitude measurements. Then you need to have the NMR measurement, and you need to measure the mass of the sample. Then let's come to relative measurements. Relative measurements can be done when you see you have something within a sample that can be used as a reference. For example, a reference can be the amount of solid. And if you want to measure some liquid, you measure the solid content, and then you measure liquid content, and then you divide liquid by the solid. And this is a way of doing some normalization. It's called, these methods are called like a methods to use relative amplitude of signals. So actually, I have written here everything. So the same: solid fat, total fat, crystallinity, water content, spin finish. Actually, many more that will be reported by Maria. So, and then absolute amplitude, relative amplitude, and relaxation times measurement. And relaxation times measurement. So everything is based on the graph that we already discussed. And there are really many applications that can be done. But for any application, you must somehow build a model. You must somehow bring the theory inside your measurement. And I guess one of the aim of our NMR Improve project is to bring the different variation, different techniques which are within the time domain NMR and NMR relaxometry into the tasks that you have when you are dealing with a dairy product. Maybe the next application I will talk very briefly can give you some ideas for your types of samples. So we are really successful in Asian market with the analyzing of surface area of particles. Just imagine you have particles with some surface area which can be active. For example, silica when you are talking about adsorbents, or ceramic particles when you are creating capacitors, or some, I don't know, some adsorbent particles that were for cosmetics or for paints, for ink. The particle within a liquid, you can imagine that liquid is interacting with the particle, and some layer around particles, the liquid is not that mobile as in a bulk condition. So the liquid near the particle is less mobile, and it has relaxation time which is shorter than the normal relaxation time of a bulk liquid. And just based on that, and based on the fact that the exchange of particle between the bulk reservoir and this liquid interface is really fast, and you will not see two components. You will see only one relaxation rate, which will be affected by the contribution of the surface. And you know, the graph is linear for relaxation rate. So the more if you have particles and you increase the concentration of these particles, the amount of this interface layer within the bulk solvent will just grow, and you will have the linear dependence of the relaxation rate, linear dependence of the relaxation rate. But if your particles have surface with more active centers for absorption, so if your surface is more, let's say, is better sorbing the liquid of the bulk solvent, then the angle of this, the slope of this line will be different. The higher slope, the stronger the higher slope, the stronger interactions between particle and the particle and the liquid. So very interesting application. We need maybe to talk more when you might have some questions. Another story is for elastomers. So as we already discussed, the stronger bounding, the less mobility, the shorter T2, the higher mobility, the longer T2. And for rubbers, it is for elastomers. This is very much important and critical. So you have more cross-linking for the rubber. You know, rubber is made out of caoutchouc by cross-linking, normally through sulfur. The more developed the cross-linking network, the lower T2 you have. Actually, I think everything. This is everything for now for the introduction. So Danuta, I guess it will be enough to somehow process inside the brain. So I made this just very simple interaction, and any questions are totally welcome.
Thank you very much.
Oh, okay. I see questions. That's perfect.
Yes. What is the weight of the equipment?
Let me put my glasses and.
The question is about the weight of the equipment. And
okay,
I lost some of the questions.
So I have very can the scalar coupling at the same time with the dipolar coupling contribute to the relaxation process? I mean, thinking about relaxivity theory.
I took the liberty to answer, but
yeah, it can. But we are talking about some parts of hertz for J coupling, and we are talking about kilohertz for the dipolar coupling. Of course, the contribution might be, but within the inhomogeneous magnet, you hardly will see it. That's the problem. Sometimes in the Earth field, when you build your house without any nail, without any metal, and you make the Earth field device, and then you measure, you can see the J coupling in the magnetic field of the Earth. Then it's possible, but really not with the typical between the isotropic. Okay, so that it was a discussion. What is the weight of the equipment shown in the video? It seems easy to sound. Is it necessary to stabilize the equipment at room temperature before measuring? So that equipment, so you will see today, you will see some parts, some pieces of equipment that we are producing. Stabilizing of temperature is essential because magnetic field normally depends on the temperature. For most of our instruments, we have the very precise temperature stabilizing system for magnets. But the guys in Finland who are producing their machines, their machine has electromagnet, and it's not that much sensitive to the temperature because the current is stabilizes, and current is the main producer of the magnetic field. That's why for their instrument it's really fast. You brought it, you plugged it in. I guess in 5 minutes, even earlier, you can start measurement. For time domain NMR machines, it might be half an hour or 1 hour to start measuring. And the weight, so the weight is normally a human can carry most of time domain NMR devices easily. Okay, maybe I missed some other questions.
There's a question about the weight, of your equipment.
Okay, maybe some questions can be addressed via voice. Via the voice.
So please answer, type or say loudly your questions.
Okay, these are good words, like words of thanks.
Okay, so what now? Leonid, thanks again a lot. And according to the agenda, we are supposed to have half of our break. What do you think about that?
Yeah, I guess. I guess it should be. It is good idea to have a kind of break. Then Maria, I guess she's ready. When maybe some people are going to come exactly as it's declared.
Okay, right? So we should start at 11, in half of hour.
Yeah. So I'm just announcing that the next session, real-time time domain NMR experiment part 1. This will not be really the real-time experiment. This will be the introduction of the experiment that can be done with a more detailed than I did. And the next session from 2 p.m. it will be real-time experiments on a real equipment, but without actually a theory. So this is
Okay.
something.
Okay. So again, thanks and see you in half of hour.
In half an hour. Yeah.
Okay. Oh, hello again. Who is with us? Everybody had coffee. Leonid, are you with us?
Yes, I'm here. Maria also is here.
Maria is also here.
Hello.
Hello. It would be nice to hear from somebody else that we have audience.
Okay. Please tell
The
me
coffee
when I can start.
normally takes more.
I mean, I suppose you can start when we get at least 3 answers in chat that people are there.
Okay.
Kahinga is there, so 1.
Kahinga, great that you are here.
But well, nobody else is responding. It's a kind of confusing. Adriana is there.
Yeah,
And Lucas. Okay. 3 replies. So
Okay, so it seems that there is somebody on the other side. So welcome.
okay. Okay, now is it visible for you?
Yes, although you might be willing to make it in the presentation mode.
Yes, sure. So okay, now
Now it's great.
Okay. So, dear participants and organizers, thank you for the opportunity to be a part of this training school. My name is Maria. I'm from Resonance Systems company. Today, I'm here to share with you the basics of time domain NMR experiments and show how to select them for your research studies, for your research demands. Today, we will also consider which of the experiments are already used in the international standards and a few practical applications. Sorry, how to remove this part?
It looks like all is okay.
Yes, because I see this panel is covering the header of my slide. Sorry.
So for us, it's okay.
Okay. This simple scheme shows some of time domain NMR applications, mostly for solid samples. The method is able to probe both structure and dynamics. When data processing and analysis, we operate with signal intensities and relaxation times. Here you see some items that is widely used in industrial sphere and academic fields, especially for solving some science tasks. So the most important is the phase composition and molecular mobility estimation. So then in the presentation, we will consider some applications where this method is applied. Okay. So about time domain NMR in solids and liquids. So it should be mentioned that direct dipole-dipole interactions between nuclei are the source of information for the method. So when we are talking about the solid and liquids, we should consider the molecular mobility. So molecular mobility can be described by correlation time. As it was mentioned in the previous report, the higher correlation time means the lower molecular mobility. So this is the difference between the solids and liquids. So what about the NMR? So when we are trying to analyze different substances in different states, we should consider some dependence. You can see it on the right side of the slide. The dependence between relaxation time times T1 and T2 and multiplication of frequency and correlation time. Here you clearly see the difference between small molecules and liquids and polymers, some proteins and large molecules. So on the left side of the graph, you see the T1 and T2 are really close each other. So, and on the right one, you see the huge difference. So this knowledge can help you to find the optimal experiment for analyzing your samples. So concerning the time parameters, time relaxation parameters, we should talk about T1 and T2, but the actual T2 for solids, we will call it T2 V star, because we cannot estimate the T2 for solid samples for some due to some limitations, which will be considered later in the presentation. So then I will pay attention to some standard experiments like free induction decay. I think all of you are already familiar with it. Then somehow the type of free induction decay, but in modified way, solid echo and magic sandwich echo. So I will show you the pulse diagrams and some features about the experiments. Then we will talk about saturation recovery and inversion recovery. So how to operate with, how to fix the longitudinal magnetization relaxation. And at the final stage of this part, we will consider Han-echo and car-partial Mayboom gel sequence experiments. So, after this, we will combine and some two-dimensional experiments based on these standard pulse sequences. So let's start with the free induction decay. This is the simplest experiment that consists of only one 90-degree pulse, radio frequency pulse. So as I already mentioned, this experiment has many modifications due to its drawbacks or disadvantages, like existing of dead time, where when we lose some NMR signal from solid part or fast decaying components, and due to magnet inhomogeneity. So researchers have been developing solid echo pulse experiment to overcome the dead time disadvantage. Here we apply two 90-degree pulses with different phases, and we record solid echo. So without losing the information about solid phase of sample. So this experiment is most effective for samples with really strong dipolar interaction with rigid domains. So another modification is magic sandwich echo, which consists of sandwich-like part of pulses, and using these pulse sequences, you will also record echo signal. So this is this experiment allows overcoming the dead time as well. So, and not to lose the solid part decaying signal. So what to add? So in the last part of today's training school, we will consider how to analyze all these raw NMR data from these experiments. Okay, so I forgot to add, sorry, here we are talking about transverse magnetization. That is the axis in transverse plane XY. So saturation recovery and inversion recovery. We cannot record the relaxation of longitudinal component directly. So we should make some action and operate with transverse magnetization. For this, if you pulse sequences were constructed, were developed, and I show you some of the simplest of them. Here you see the inversion recovery, where we apply as the first radio frequency pulse and make the longitudinal magnetization align how to say emo. I forgot the word, sorry. Minus the taxes. In saturation recovery, another story, here we rotate the longitudinal magnetization into the transverse plane. So, and these two experiments are multi-step. It means we vary the time parameters, especially tau, and record the free induction decay. So after the second 90-degree pulse. So it means we make acquisition in the transverse plane. So after, when we record free induction decay, we estimate the average feed amplitude. So, and on the right on the right side of the slide, you see the final T1 curves. So it means the how the longitudinal magnetization is recovered. So these points are the average feed amplitudes recorded for each time step, for each tau value. So you see the difference between the inversion recovery curve and saturation recovery curve. So because of the first pulse, the inverse P pulse rotate the magnetization to minus align to minus Z minus Z axis. I hope you understand what I mean. Sorry, I haven't added this picture here. And this second experiment align rotate to transverse plane. So, and you see the points have the positive values. So this experiment can be widened, and you can easily estimate the contribution of different phases. So for complex samples, for example, you want to analyze polycrystalline polymers, which consist of crystalline and amorphous phases. In this case, you can easily select the range for averaging the amplitudes and build the separate T1 curves. But at the final stage, you should remember that highlighting, for example, highlighting of amorphous component, you should consider only that amplitude where the solid component was already relaxed. So no signal from the solid, crystalline component.
So Maria, don't you need to change the picture to show the averaging areas?
I have no this picture. So I won't just explain, but I need some help. Okay.
The idea to measure T1 of different parts of samples. You can measure T1 of solid, or you can measure T1 of liquid part of a sample, depending on how you tune the instrument. Whether you select for averaging something on the short component, fast decaying on solid, or on liquid. This is somehow like in spectroscopy. In spectroscopy, you can tune to different spectral lines and see their different T1 behavior. And here, we also tune to different parts of the signal with different mobility. We also can see their different T1 contribution. Something like this.
Okay, just to summarize the information from this slide. We operate with two different experiment: inversion recovery and saturation recovery. In both experiments, we record, we acquire feed and record the average amplitude of feed depending on the tau step. So this is the main idea. So to differentiate the different phase contributions, we should put different time range for amplitude averaging, sorry. And we should consider firstly the total amplitude, where we see the contribution from all phases: crystalline, for example, medium, interface, sorry, and amorphous phases. So if we want to differentiate the contribution of amorphous, we should consider only that part of signal where the magnetization of amorphous component is not zero, so is more than zero. So the same for another phases, but especially for crystalline, for example, we should subtract the contribution from interface and amorphous phases, just to see the crystalline phase contribution. I mean from the total amplitude. So let's continue. For measuring the spin-spin relaxation time in systems with the high molecular mobility and short correlation times, we apply echo sequences like Han echo, or in other words, spin echo, and CPMG, car parcel Mayboom Jill sequence. So you see the Han echo consists simply of two radio frequency pulses. So after applying the first 90-degree pulse, we record the feed free induction decay signal. When we applied the second pulse sequence, we after time tau, we record the spin echo. So this experiment can be multi-step as T1. And if we will vary the tau value and record the echo amplitude with varying tau, we will get exponentially decaying signal. If we will feed it, we can obtain the true spin-spin relaxation time. This experiment is effective for samples with liquid-like or somehow liquid phases. So another experiment is CPMG. You see the first part of the experiment repeats the Han echo, especially 90-degree pulse and P pulse. So in this experiment, you will get the train of echo signals, and if you will connect the peak of the echo signals, you will also obtain the similar exponential decaying curve. So what I can add here, the Han echo sequence has is longer. I mean, in longer to perform. Something like this. Now, I want to say you about two-dimensional experiments. Here we can combine some standard experiments and simultaneously get T1 and T2 parameters. For example, on the left side, there is a picture of inversion recovery Karapasyan Mayboom Gill combination, which allows estimating T1 and T2 simultaneously. You can easily combine different experiments, but you should know for what you want to do this. So inversion recovery CPMG pulse sequence is usually applied for constructing the T1 T2 correlation maps. So and used for analysis of porous media, where you can easily observe the T2 distribution. So another third-dimensional experiment is the combination of saturation recovery and magic sandwich echo. So for each tau 0, you record magic sandwich echo decay. And at the final stage, the longitudinal longitudinal magnetization recovery curve will be recorded with saved MSC decays. So this experiment is effective for solid samples, more effective for solid samples, as I mentioned above. Concern spin diffusion. In the signal of in the transverse magnetization decay signals, of complex samples, as a rule, you can observe a separation between fast and slow decaying components. So if there is more than one phase, it is easier to use a spin diffusion experiment to highlight one of the phases, or one of the existing phases. So, for example, Goldman-Shen experiments is used for mobile domains highlighting. So, double quantum sequence is for rigid domains. In Goldman-Shen experiment, we apply three 90-degree pulses. The time between first and second is fixed from the user side. So how to select the right tau time? In the experiment, we are talking about of transfer the magnetization between mobile and rigid domains. So for this, we should find the time point where the fast decaying component is zero. So it means there is the signal of mobile soft domains, and there is no the signal of solid signals from solid domains.
Ci sei? Vieni, vieni. Vieni, vieni.
So
Se
then
riesci.
when
no,
the
stavo
fast decay
Sì, sono collegato, ma è con la scuola base.
Sorry, dear all, could you please switch off your microphone?
Ok.
Colleagues from Italy, please do switch off your microphone.
Roberto, prego, silenzio.
Non è cambiata anche la situazione.
Thank you.
Ho riportato la risposta, siccome una delle risposte, cioè del medico componente è stata, io non posso fare niente. Ma se arriva una
Our dear colleagues from Italy, please do switch off your microphone. We are not able to continue.
Mi sto tirando la zappa sui piedi perché non è una cosa facile, ma almeno se abbiamo una
Dear colleagues from Italy,
delle dimostranze da parte di qualcosa che... Scusate.
C'ho il microfono aperto.
dear colleagues from Italy, please do switch off your microphone. We are not able to continue. Okay, thank you very much. So Masha, I think you can continue.
Thank you. When the signal from fast decaying component is zero, we rotate the existing signal, the existing magnetization of mobile domains to that plane, and the magnetization from mobile phase will transfer to that one of solid phase. So varying the tau as di parameter, we will record the free induction decay with varying amplitude. So the final curve will be will look like this. At this graph, you see the points with black squared points for Goldman-Shen experiment on cotton cellulose. So we vary the time between the second and third pulses. and record the average amplitude of feet. So the second experiment for spin diffusion is a double quantum sequence with varying time parameter for spin diffusion. You see this TZ on the path diagram. So here we use some double quantum filter time excitation, T excitation, and T reconversion. This parameter is selected like in the range of 10-20 microseconds for polymers, especially because of the condition, because of the maximum of double quantum curve is in this range. So then we are trying to look at the stronger dipole interaction and varying the TZ parameter. And we will observe the opposite situation when the spin diffusion from rigid domains will transfer to mobile domains. So, and records the circle red points on the graph. So the curve will be growing. So now I suggest to continue with some standard applications. I mean applications related with international standards. The first one is solid fat content with ISO 8292, animal and vegetable fats and oils, determination of solid fat content by pulsed NMR. There are two approaches, direct and indirect. So let's consider the direct one. In simple words, we record free induction decay. So, and consider 2 points. First point is for solid and liquid signal marked as S11. 11 means the time where there is a signal from solid and liquid phases. And the second point is S70. 70, this is the time, 70 microseconds. This is the time where the liquid signal is observed, only liquid signal. So due to some the disadvantage of the method, the F factor is the F factor should be considered too. So F factor allows estimating the total signal from solid and liquid in the 0 point. This point is marked as 0. So SFC is the ratio between the difference total minus liquid. So this means the solid, only solid signal, divided by total solid and liquid signals multiplied by 100%. So A0 can be written as the signal from liquid solid and recovered the solid signal. And the final equation is consisted of the recovered only solid signal divided by the total signal. This is the simple explanation of the method. Okay. On the slide, you see the recorded melting curves measured by direct method. So for stirring different oils, different samples measured on spin track. But this method can have some disadvantages. And the second approach, indirect method, can be used too. For the okay, I forgot to add. As disadvantages of direct method, some contribution from fast decaying component can be calculated too. And to avoid this, some manufacturers recommend to use indirect method. For indirect one, only the signal of the liquid phase is used. The signal of the molten and the signal of the molten and the crystallite sample, as well as the signal of a reference at the same temperature is measured. The values of the reference are needed for temperature correction. As reference oils, which are liquid at the measured temperature range, for example, sunflower oil can be applied. Additionally, here we compare just the molten fat phase without the solid fat contribution. Another standard experiment is the water and seeds, oil in seeds. This is the standard. This is the standard is ISO 10565, all seeds simultaneous determination of oil and water contents method using pulsed nuclear magnetic resonance spectrometry. So the experiment is simple. We just record feed Han echo experiment, as we have already known from the last slides. From the first 90-degree pulse, oil sum of oil and water signals is signal recorded, and after p-pulse, the oil signal as echo or spin echo signal is acquired. Thus, we can differentiate the contribution of oil and water and build the separate calibration curves. In the calibration, the known or reference part or moisture content matches the NMR value recorded by NMR system. Another essential application is the droplet size distribution by pulsed field gradient NMR. This application is special for water in oil and oil in water emulsions. Here you see the simple schematic representation of the experiments. In the A, it is pulse field gradient spin echo. We have already know that 90-degree and P pulses give us the spin echo, but the difference is in the application of gradient pulses with amplitude G and duration theta. The time and the special time between these two pulses. On the second picture, this pulse field gradient stimulated echo is presented. This experiment includes three 90-degree pulses with the same phase. This pulse diagram is allows obtaining the echo 2, but the difference between these two experiments in them in that the P pulse split it on the two pulses, two 90-degree pulses. Applying the pulses, we record spin diffusion decaying curves, which then processed by special algorithm like long norm distribution with known model. And after this, the droplet size distribution can be obtained. On the slide, on the right side of the slide, you see the example from the literature. Water droplet radius for water in crude oil emulsion stability analysis. How the radius was changed during the time. This distribution method is most effective when the user wants to know about emulsion stabilizer conditions and for some food applications. The next application is the spin finish. This is a critical or key parameter for fibers, yarn, and its role is in increasing antistatic properties and creating interfilament cohesion, which improving the quality of the final fiber product. The experiment for spin finish estimation is simple. It is the same as for water and oil in seeds. We record feed and spin echo. There are two types of analysis, weighting and weightless. So in weightless, we just find the ratio between echoes from spin echo signal from oil to total amplitude for all sample components, including fiber and probably some another component. In the weighting, we matching between the known value of spin finish in weighting, firstly, we weight the sample, then measure the amplitude, and we match between the mass and the amplitude, measured amplitude, and doing the calibration. On the slide, there is a calibration example for spin track. You see the calibration is linear, almost linear. Okay. And it shows that the analysis is straightforward and simple. And one of the last standard application is hydrogen in foil, called ASTM D7171. Standard test method for hydrogen content of middle distillate petroleum products. So by NMR. The experiment is also very simple. It's feed. The same as for solid fat content. But here, there is only one type of analysis. It's weighting. And before the measurement, we shoot the weight of sample and conditioning at required temperature. Then we acquire the feed, record the averaged amplitude, and make some calculations, get the linear curve between the hydrogen content and NMR value. NMR value, as you see on the slide. Quality control of polyolefins. This section is essential for polycrystalline samples too, not only for polyolefins. It can be NMR, as I mentioned on the second slide, NMR easily estimates the phase composition of complex samples. Here, if we are talking about the polypropylene, polyethylene, there is some ratio between crystalline and amorphous, and sometimes between interface contents. And to estimate the xylene soluble fraction of polypropylene, for example, it can be done the calculation of amorphicity. It means for the simple way, it can be calculated by the ratio of signal intensity from amorphous phase and the sum of amorphous and crystalline phases. Signal intensities or amplitudes can be easily estimated by two ways. By averaging method or by fitting. But the averaging method, like in solid fat content, is the easiest and more preferable and more accurate, because some NMR signals cannot be accurate fitted by the models. And crystallinity of polyethylene. So the approach is the same, but crystallinity is determined by the ratio of crystalline amplitude or signal intensity from crystalline phases to the sum of amplitudes. On the right side of slide, the calibration between xylene solubles in polypropylene from reference values or known from wet chemistry versus the NMR data. So the dependence is clearly linear, and analysis in general is simple and fast and doesn't require any solvents and a long condition. Can we make a break, probably?
This is a fantastic lecture, Masha.
No.
Yes, it is. You know, I cannot, the examples are really, really, really fantastic. Well, you said you wish to break. Let us,
because
yes,
of
answer is of course sure, but let us plan, because according to the agenda, we are supposed to be here until 1 p.m. and then have a break from 1 to 2.
Okay, 5-minute break.
The idea maybe just people are tired to listen to two hours. Just make a 5 minutes break and then just continue.
But let me tell one thing. How much more time you need? Because maybe we can make a longer break.
About 50 minutes, right, Masha? 40, 50 minutes.
Something like this, yes.
So how about making, I don't know, 15 minutes break?
Yeah, maybe what's important that people would come back after the break. This would be great.
So, okay, but I think 15 minutes is really okay. So let us meet. Let us meet at 12:15, okay?
12:15, yeah.
Then we'll have like half of hour, and then we'll still have time for lunch.
Yeah, great.
Okay. Masha, it's great, really.
No, I know.
I learned a
No.
lot. Okay, you need break, so I'm going
Huh?
off.
Yeah.
Already the okay. We have already the examples of successful using this method. Here we can see the particles. We can see on the picture the particles that have that are placed in the solvent, and there is some interface layer between the particle and the bulk liquid. So this interface layer is built by the solvent monolayer, usually by solvent monolayer. Here, the relaxation times is lower compared to bulk liquid because of interface layer molecules are restricted in the motions due to connections with surface particles molecules. So meantime, different relaxation time due to fast exchange between the molecules in interface layer and in bulk liquid goes to the fast exchange, and thus the one exponential component is observed. So using the fast exchange condition, this method can be can cover some particle parameters like wetted surface area, particles concentration, wettability and dispersibility, surfactant and dispersant efficiency, as well as particle solvent affinity. So simply, it can be compared. For example, different particle solvent systems can be easily compared based on the relaxation rates or relaxation times. Here I put the example. I have done measurements of relaxation rates for colloidal silica water suspension AS30 obtained from sigma aldrich with different surface area, specific surface area. And you see the clear linear dependence between the relaxation rate and surface area. So measuring 2 points, you can easily estimate the mentioned characteristics, but some calibration procedure is required. Porosity and pore size distribution of porous materials. In porous media, in porous materials, the most important application is, in my opinion, is car parcel Maeboom Gill sequence, CPMG sequence. So for this analysis, the researcher should saturate the porous materials with probe molecules. For example, it can be water, simple water molecules. So after saturation, researchers put the sample inside the magnet and record the CPMG decay. After that, CPMG decay is should be processed by ILT algorithm. ILT means inverse Laplace transform. And after this step, ILT will give the T2 distribution. So why T2 distribution? When we saturate the sample, the samples normally have pores with different diameters, with different sizes. So, and for this analysis, it is essential to saturate the sample fully. So, and get the signals from probe molecules from each pore size. So when you will get the T2 distribution, you can easily correlate this T2 distribution with pore radius. For this, I put here the main equation where the relaxation rate is related with T2, relaxation rate of bulk. Bulk liquid means where liquid that has no restriction in motions. Then diffusive part and surface part. So relaxation rate of surface is more than the relaxation rate of bulk because of NMR relaxation times of bulk is here the relaxation rate of surface is predominantly influence on the full picture. So we after simplification we get the simple equation that relate the pore size with the T2 with spin-spin relaxation time. But you see the coefficient C is unknown, usually unknown, but it is also requires some calibration. So, but but the analysis is straightforward and simple to perform and to understand. Another type of NMR experiment for estimation the pore size distribution is NMR cryopyrometry. Here, in addition to benchtop NMR analyzer, a variable temperature probe is required. So for this analysis, we use special system which varies the temperature from, for example, 40 degrees till the minus 60 degrees Celsius. So the main idea of this approach is to saturate the porous materials with probe molecules. For example, for small pores with diameter less than 10 nanometers, it can be used water molecules. So for another one, for example, for another pore size range, it can be used another one, which will be most effective for the interesting range. Then after saturation, we start to vary to low, decrease the temperature, and during the cooling or freezing procedure, we should record the signal from liquid and in pores. After some time, you can easily observe the hysteresis phenomenon. So here I put some examples for zeolites melting and freezing and melting profile recorded from 5 degrees till minus 80 degrees. And for better understanding, for more accurate estimation of pore size distribution, the experts recommend to analyze the melting curve. So, but some samples doesn't have the hysteresis like cellulose. We have measured zeolite, which was saturated with water and cellulose. And for zeolite, we got, as you can see, we got the hysteresis, the clear, observable, but for cellulose, no. So we see that the pore system probably of cellulose is more flexible. So, coming back to the slide with equations, the NMR clear is based on two equations. The Gibbs-Thompson equations that maps the melting point depression to pore size, and the Strange-Drachman-Smith equation that maps the melting signal amplitude at a particular temperature to probe volume. Gibbs-Thompson effect means that small crystals of a liquid in the pores melt at a lower temperature than the bulk liquid. And you see that melting point depression is inversely proportional to the pore size. So it means for each temperature, the system record echo signal from the liquid. So why echo? Because using the echoes, we can easily differentiate the signal from existing liquid and the signal from ice. Then here on the Strange-Rachman-Smith equation, by V we understand the intensity of liquid signals. So when the measurements are done, the simple conversion by Gibbs-Thompson equation can be performed, and after converting the axis, the temperature axis to size axis, Strange-Rachman-Smith equation will give the pore size distribution. But again, this approach requires preliminary calibration. For Gibbs-Thompson coefficient, some scientific particles have, scientific papers have tables with already known coefficients for different solvents. So, and you can easily use it for your measurements. Okay, let me just summarize this approach again. First, the suitable probe molecule is selected. Then, second, the porous material is saturated by these probe molecules. So at the third step, saturated porous material measured with varying temperature, measured the freezing melting profile. After this, the melting curve is analyzed by the Strange-Rachman-Smith equation, and with the Thomson-Gibbs equation just for transfer the temperature axis to pore size axis. So these are the examples of our measurements. And I think it's the last, probably about polymer adsorbed water system. We have some experience with cotton cellulose and with studying the interaction between cellulose and water. So the cellulose sample with water has a complex form. I mean, the pre-induction decay of the sample has complex form. It contains the rigid component, fast decaying, and the long component, slow decaying. It can be easily they can be easily subtracted for separate estimation. We will talk about the method for differentiation later, but here I also present the results of estimation, the crystallinity and morphicity for cotton cellulose with different moisture contents. And you see that increasing the water content is going to increase the amorphicity and decrease the crystallinity. So for such systems, it is also possible to record the water sorption isotherms. So just put your samples in desiccators with different water activity and measure free induction decay. Use the special formula for transfer the water, the NMR data to water content and build the water content depending on the water activity. Bakery products. This is a still developing field of NMR applications. And when people talking about bakery products, we usually think about the starch and water interactions. So it's true, and most of papers, in most of papers about the bakery products and NMR, we see that researchers trying to understand how water interact with starch and how water influences on starch structure during the baking, during the storage, and about starch gelatinization and other topics. So, but on the site, I also show you the view of researchers, the view about water mobility and mixture structure of gluten network that is developed during the dough mixing. So, and ILT T2 distribution after ILT procedure will clearly shows a different water populations, and authors trying to understand and trying to relate the observed hydration state with the stage of gluten network development. And some pictures how they about their opinion about the developing the networks. So in these applications, the main indicator is water, and usually researchers monitor the interaction between components with dough components or just starch based on the water rate distribution or distribution. Okay, seems. Thank you to all of you for your attention. And if you have any questions, I will be very happy to answer them.
Thank you. You know, it's beyond our expectations, let's say, because you have shown already so many examples of applications. So it shows that time domain NMR is really the highly appropriate and very, very beneficial method for our project. I'm overwhelmed myself with the amount of applications. and very grateful to you.
Thank you.
You know, I have a kind of idea, but
Okay.
then the next part will be a life experiment, yeah, which somehow is quite demanding. How about we go for a good lunch and meet at 2 p.m. And then anyway, after demonstrating how the experiment works, they will be time for discussions still, and you will be there. So I would just propose to shift the question for later, because people also must think a little bit more.
Okay.
So I propose that we go for lunch and we meet at 2 p.m.
Yeah.
Okay?
Yeah.
Mhm.
Yeah, really good.
Thanks.
Yeah, bon appetit to everybody.
Thank you.